Okay, welcome. Today we're going to talk about the interaction of ionizing radiation with tissue. First, we're going to ask the question, what is the basic mechanism of contrast for X-ray imaging? And then we'll ask the question, what are the basic mechanisms for interaction between ionizing radiation and tissue? Third topic will be, how does this interaction depend on the tissue? And finally, we'll end with a primer on radio protection. So a short introduction on how do we protect ourselves against X-rays. So let's start with first some examples. And this is a sped up video just to come back to the generation of X-rays. And that's a standard X-ray tube like we've seen last week, the anode, the cathode, and the electrons that are accelerated, which impart on the anode. Then we have the shield, and the X-rays are emitted. So they are, in this case, sent to the arm. You can see the person is here protected. The X-rays penetrate the arm. And then at the end, in a conventional X-ray, you get the X-ray image. And here in this case, there's a fracture. Okay, sorry for the Mickey Mouse sound. So, X-ray imaging, this is an example of a mouse imaged here. We don't see much here. We can see the legs, we can see the tail, you can see the bones already, so you can see some contrast in this case. And actually, if you display the image, window it differently, you can actually see the skeleton of the mouse here. So these are the legs, the four legs, the rib cage, the tail, and the spine, and here's the skull. With X-rays, well, one of the features, one can go actually to very high spatial resolution. This is an X-ray image of a mosquito that's been taken. So here's the head, the wings are here, and you can see the tails, the legs. Or even higher spatial resolution, this is now the image of a normal red blood cell, and these are infected red blood cells infected with a malaria parasite. Or even going further down to smaller cells, this is a virus, the H1N1 virus for the flu. Now, at this resolution, you start to see the structure of the cell surface, and here, particularly, its receptors or with which it connects. So what do we need for bioimaging? So we need contrast. And in this case, contrast is absorption of X-rays. We've already seen some examples. We see the differences between bone and tissue. We see the difference between a mosquito and air. We see also here differential absorption of X-rays. So how can we describe the absorption of X-rays? We'll start out with a very basic introduction with a basic term. So first, what are the fates of the photon that hits the tissue? Well, for one, it can just go through. We'll forget about that because that's not useful. That doesn't give us any information. Then we have absorption. So absorption of the photon, that means its energy is absorbed by the lattice, by the tissue. The third effect is scattering. Or if these two, that where the photon does not come through the tissue, either it's absorption or scattering. So let's look at a tissue layer of delta X thickness, and let's assume we have n photons that impart on this tissue layer. Since absorption scattering removes photons from the beam here, we will end up at the end with n minus delta n photons. Okay, so the number of photons is reduced by having this X-ray beam passing through this tissue of layer delta X. So now the removal of the photons is done by probability, and we can write an equation that describes the number of photons that are absorbed or scattered, that is removed from the beam, the delta n, in a layer of thickness delta X. And this is very empirical here. So we define that the number of photons are removed is proportional to the thickness of the layer. That makes sense. It's probability. If the layer is twice as thick, the probability that the photons are removed is twice as high. The number of photons being removed, if we have, instead of 100 photons, 200, there's also going to be, instead of 10 photons removed, for example, 20 photons removed. And then here is a constant mu here, and we're going to talk about this constant in more detail during this lecture. That is a property of the tissue. It just basically describes the probability with which this happens. And of course, delta n here, we're setting it to negative, so we should actually write here n plus delta n. Okay, now this constant here, mu, is called the linear attenuation coefficient. Okay, linear because just this equation that defines its existence is a linear equation. That's why it's called linear attenuation coefficient, and it has units in which it is commonly described as 1/centimeter. Now what we will see is that this linear attenuation coefficient depends in a relatively complex way on the energy of the photons, the atomic number, and the density of the electrons in the tissue. So it's a function of these three parameters. So now let's assume we'll let this layer of tissue, delta X, go to 0. And we'll have the number of photons now become a function of position. So that is reasonable to assume, because if we have passed through a number of layers, there is less photons. So the number of photons that a certain layer, delta X, sees is a function of its position in tissue. Then we can rewrite this equation here and say, okay, the number of photons removed is negative because they're being removed, times the constant, times the number of photons hitting the tissue, times the thickness of the layer. And here we'll just let it go to 0. So we'll put the infinitesimal description here. So I'll take this equation here, I'll divide by dx. So I get now this first order differential equation. And well, we are all familiar with its solution. This is in the exponential function here. So in this case, we can say the number of photons at position x is equal to the number of photons arriving at the tissue or at the organism times the exponent of minus mu x. Now here, the caveat is, what we've assumed that the linear attenuation coefficient is constant in position. So it's constant with x. So that's valid. That's a simple situation. That's valid for a tissue or for a sample where its makeup does not depend on position. But that just makes the mathematical expression easier here. So in this case. Okay, now there is a definition I want to introduce, and that's the half-value layer. The linear attenuation coefficient in units of 1/centimeter is not an intuitive term. We can't really grasp what it means. At least I can't think in 1/centimeters. I can think in centimeters. So we're going to now define the half-value layer, and that's basically the thickness of the material that removes half of the photons. So what it just means is the number of photons for a tissue of a thickness that corresponds to the half-value layer is equal to half the photons that arrive at the tissue or at the material. So then we just plug this into this equation here. We have it here. Solve it, and then we can see that the half-value layer is equals to roughly 0.7 divided by the linear attenuation coefficient. But the nice thing is it now has units of centimeter. So now we can visualize the effect of absorption of photons by looking at the half-value layer, and this allows us to more intuitively understand the effectiveness of absorption. So to give you some ideas, the half-value layer is on the order of several centimeters for tissues. It is roughly 1 to 2 centimeters for aluminum and 0.3 centimeters for lead. Hence, if you go for an X-ray scan of your arm, they're going to put some coats on you that are very heavy. They're filled with lead. So they have lead has a good absorption quality. So what are now some typical attenuation coefficients? Well, now we're going back to the linear attenuation coefficient, and here are some materials to give us an idea what we're talking about. Here's the hydrogen, and then we have the density. We have water vapor, we have air, fat, ice, water, and compact bone. The second column here is the number of electrons per unit mass. In this case, it's per gram, and you can see there is quite a difference. We have per gram, we have quite a few electrons here, and for bone here. But then if we express the electron density per volume, this is a different story. Now we can see here there's quite a bit difference with bone the highest, and these are the corresponding linear attenuation coefficients for these types of materials. So now what we see here, if you look at water, we divide the linear attenuation coefficient by the density of water, and we divide the linear attenuation coefficient of ice by the density of ice. We actually find that these two are very similar. So the density is roughly of ice is about 90% of water, and this linear attenuation coefficient is roughly 90% of water. So this is another way of normalizing this constant that describes the material to be independent of its density, and that is the mass attenuation coefficient. It's given by the linear attenuation coefficient divided by the density of the tissue. It has unit centimeter squared per gram, and so it is constant for all forms of that particular substance. So here the example of water. So now it describes a property of the element, not necessarily of its state. So that's the mass attenuation coefficient. So why do we need more sunscreen when we go into the mountains? There's less air, yes. And then what else? The attenuation is lower, yes. So it's less air. So it's the thickness of the layer. That's correct. That's different. There's something else. It's also thinner. So even in terms of distance, it is less. On top of that, the air is thinner. So you have less electrons that can remove the ultraviolet. Okay, so what are the possible interactions of X-rays with biological tissue? And we actually decide here, differentiate here 4 fundamental interactions. Number 1 is Rayleigh scattering. So we have an incident photon that's being scattered at a certain angle. And Rayleigh scattering occurs only if the particles are much smaller than the wavelength of light. So that's a requirement that we have Rayleigh scattering. So that's the condition here, that the dimensions of the object are smaller than the wavelength. It's an elastic scattering, so the light does not change its wavelength. So whatever color it has coming in, it's the same color coming out. And there is no ionization occurring, so it's classical scattering. Okay, so the intensity, now we can see here, this is an expression I just took from the literature. The intensity of the scattering depends on a number of factors. It depends on the angle. It depends also on the wavelength. So if we simplify that just to see the major parameters, we have something that's angle dependent and something that's wavelength dependent. So actually what it means is the wavelength is below, it means that the shorter the wavelength, the more scattering occurs. So the short wavelengths are being more scattered. So here's the observer at a certain angle, and the intensity is stronger if the wavelength is shorter. So let's see some example. You can actually see Rayleigh scattering in your bathtub. You see it actually at Lake Geneva as well. You know, if you look at the water, just at the water straight, it's clear. But when you look at the lake is blue. Now blue has shorter wavelengths, so light is being scattered at the shorter wavelength. That's scattered light. So if you look at the bathtub here, when you see it fill up or go down, you see how the intensity of the color changes. So if it's thicker, there's more scattering of the blue light from the room there. Other example is blue sky. That's sunlight, which is essentially white. We just see the blue light, so we have a blue sky. Conversely, Rayleigh scattering is the reason why we have these beautiful sunsets. If we have rain coming, so if there's humidity in the air, or if we have pollution, if there is smog. And then there are particles in the air. And why is it red and not blue? Because we are, in the sunset, we are in a straight line of the light, and the blue light is more scattered, so it takes out of the white spectrum the blue light. So that's a manifestation of Rayleigh scattering that we see basically every day. So I thought we could do a little experiment here and actually try to reproduce the effect. So the effect of scattering the short wavelengths and the red light passing through. So what I have here is a container of water. I'm going to put in some substance. I forgot what it is, but basically we'll start the reaction and produce colloid particles that have dimensions larger than the wavelength. And as they will form, you will see how the light changes. So we'll see the light here of the water. It's clear. We see the light going through. It's reflected by a mirror, and you see it here on the wall. It's also clear. Okay, so we'll have to wait a little bit for the chemical reaction to occur. We should start seeing this part becoming blue and this part becoming yellowish in a few seconds. I think we're starting to already see it turn a bit yellowish on the wall. So that's where the sun is. It's around 5 o'clock in the evening. Sun is already not exactly white. And we'll give it some time to produce the reaction. Okay. Well, do you think it's getting a little bit yellow? With a lot of imagination. See, when I did this experiment last year, it was so fast that we couldn't actually film it properly. Now I have to just hope it's going to happen a bit, not too fast, but also not too slow either. We'll give it, yeah, no, I think now it's clearly getting yellow. No? Or is it just my wishful thinking? No. Okay, now it's clear, right? You can see now it's blue. So that's the white light. The red light is removed because that's going there. It's just the blue light's being scattered. And now this guy is going to start to turn more and more towards red. Yeah, now we can see it very clearly. This is blue. This is getting towards orange. So we'll soon have a very nice sunset in the lecture hall. Now, what do you think in what state we will end? Yeah, it's a trick question. So these colloid particles are going to form. There's more of them that are going to form. There's more scattering and so on. So in what state are we going to end?
White and red.
White and red. Yeah, now you can see. Yeah, that's a nice sunset. It was like the sun last night, the moon last night. It was really nice. Or was it this morning out in the west? It was really very orange. You'll see it's getting more and more red, but also darker and darker because less and less light goes through. So actually the end state will be reminiscent of which city? The weather in which city? Okay, you probably don't know that. But which city has a lot of smog?
Beijing.
Beijing, yes. So actually in the end this will turn out to be just like Beijing. You see now, you will really see hardly any sun there. And this part here in the end, there will be no light going through. It's like when you're in Beijing, you're seeing about 30 meters distance. It's not fog, it's smog. It's pretty impressive if you ever go to Beijing. You actually have it in the terminal of the airport. Okay, so yeah, sunset is happening. This one has been a success. Okay, so there is the condition for Rayleigh scattering to occur, and that is that the dimensions of the scatterer are bigger than the wavelength. So now let's look at X-rays. So for X-rays, for X-ray imaging, Rayleigh scattering, because its scattering has a deleterious effect on image quality, and therefore it's not very welcome. Fortunately for us, it has a very low probability in X-ray imaging. It's about 5%, so it's not a very important effect. And actually, we can calculate from the relationship between energy and wavelength, we know the energy of the X-rays, we can calculate the wavelength. And so we have actually, for 100 kilo electron volt with this expression I introduced last week, we can calculate the wavelength is 0.012 nanometers. Okay, that's less than an angstrom. And we had the requirement here that the size of the scatterer should be much smaller than the wavelength. So there's actually nothing in X-ray at these energies that is small enough to produce Rayleigh scattering. The atoms are too big, so that's why it has a very low probability for imaging. Okay, now we can see we are in Beijing. No more light. Nothing goes through anymore. And what you see is just the smog of the city from the coal plants. Okay, so this condition of the wavelength being much larger than the scatter implies that the scatter for X-ray imaging should be very small. Now, the second effect I want to talk about is Compton scattering. So now we have an X-ray that comes to our atom, interacts with the electron, outer shell electron, and is being scattered. So here's an example of a Compton electron. So this is a cloud chamber where an X-ray came in from this end, liberated an electron, and the electron now ionizes the cloud. And this is a spiral form because this happens in a magnetic field. So we'll do that experiment later. So Now, Compton scattering occurs at the outer shell electrons. It's an effect that's largely limited to the outer shell electrons. Since it's an interaction of the X-ray with the electrons, it actually results in ionization of the atom. So basically, when you're looking at it, you got the X-ray coming in, here's the electron, the outer shell electron. It's kicked off with a certain energy, and the photon is deviated. We'll assume here that the electron is at rest and takes up some of the energy from the photon. So that's the basic mechanism here. Now, if we're talking about outer shell electrons, we still have some binding energy. But in this process and what will follow, we will neglect the binding energy. Why would we neglect the binding energy of the outer shell electron? Well, we'll make just the assumption that the energy of the photon is so much higher than the binding energy of the electron that we can neglect it. Just has to be much larger. Okay, and the Compton effect is named after Sir Arthur Holly Compton, who got for this discovery the Nobel Prize in 1927. The scattered photon then, of course, will continue to interact with the tissue with subsequent interactions like Compton scattering, Rayleigh, or the photoelectric effect that we'll discuss shortly. The probability of Compton scattering increases with the photon energy and with the electron density. Okay, photon energy, that's logical. I mean, electron density is logical. The more electrons we have, the higher the probability that a photon will collide with an electron. Now, typically, the electron to mass density in tissues is pretty much constant. It's independent of the atomic number. So actually, the Compton effect is pretty much proportional to the density of the material. Okay, so now I want to derive some important relationships that we're going to use in the subsequent lectures. And so we'll do a brief tour back to first-year physics. Here's the photon, here's the electron. Photon makes a collision with the electron and is deviated by the angle theta. The electron gains some energy. So we have the definition of linear momentum, the relativistic definition we will use here. So it's mass times velocity, and for mass we use the relativistic mass. And now here we can calculate the norm of the linear momentum. And then we can express this in terms of the energy. This is just an equation here. We'll use relativistic energy here. That's this term. We'll subtract this term out. That's just multiplied here, so we have the same denominator. And now we reshuffle the terms here, and we'll find that this is equal to linear momentum times the speed of light squared. So in the end, the linear momentum squared, that is the norm of the linear momentum, the magnitude of linear momentum squared, has a relationship to the energy of the object squared divided by speed of light minus m0 squared c squared. So that's just going from this expression here down to here because this is pc squared here. So that's just using these terms. Okay, now what about the photon? The photon carries energy, obviously, solarium being outside, the sun heats us, it does it with photons, so they must carry energy. But it moves at the speed of light, so the photon is a particle, if you will, that has no rest mass. So if you were to travel with the photon at its speed, you would not see any mass. But now from this relationship here, we can use the same relationship here, so we have no rest mass. We can calculate a relationship between linear momentum and the energy of the photon. Basically means the energy of the photon divided by the speed of light, that gives us the magnitude of the linear momentum of the photon. And that we are going to use to analyze this elastic collision between a photon and an electron. Okay, so actually the Compton effect is nothing but a simple elastic relativistic collision between a massless particle, light, a photon, and an electron. So for elastic collision, we have conservation of energy. This is before, this is after. So the energy of the electron is equals to the energy of the photon, and this is the energy of the electron before it's at rest. This is EF is energy final, that's the energy of the photon afterwards, and EE is the energy of the electron afterwards. With conservation of linear momentum, again, before and after, we'll assume the electron is at rest, so it has no linear momentum, and we express the linear momentum of the electron as part of the change in linear momentum of the photon. Now we use the expression that I derived on the previous slide here. We'll use these two laws of conservation, and then we do some math, which I'm not going to do here. You have it as a complement in the handouts. It's relatively straightforward, but cumbersome and takes time, so I don't want to use this time here. But now we get the relationship between the energy of the photon after the collision related to the energy of the photon before the collision, and here comes the term cosine theta, depends on the deviation of the angle. If we express this in terms of wavelength, that sometimes is done, then the wavelength of the photon after the collision minus the wavelength before the collision is expressed by this relationship here with Planck's constant. So that's another way to express it. So what can we deduce from this equation here? The energy of the photon is maximal if the angle is theta, so there's no scattering, and then in that case we find that the photon has not lost any energy. It's minimal if the theta is 180 degrees, or pi. That's backscattering of the photon, and in this case we have the minimum energy of the photon is given by this expression here. That's just putting cosine theta to pi in this expression. A particular case I want to just bring up here is, what if the photon is exactly the rest energy of the electron, MEC squared? We can look at it in this case, and then we get MEC squared over 2 minus cosine theta. Okay, so now a particular characteristic of the Compton effect is that its effect, change in photon energy, final energy related to initial energy, depends on the angle, but it also depends on the initial energy. So here we have the example of metastable technetium-99. There's the energy of the photon that is considered here relative to the rest energy of the electron is 0.27, and for positron emission tomography, this is the effect here. So we'll see an effect of scattering of the photons that depends on the angle, so the energy of the photons that are being scattered depend on the angle being observed. So this is the Compton effect is here. The experiment. So we should be able to hear this, and you should see it on the screen what's happening here. So I have a source of X-rays. We've seen that, how we're doing that last year. Okay, so now what you see on the screen here is 1,400 incidents per second. And now we can hear it. So what this measures is the energy of the photons that are coming through. And now I'm almost at 0 degrees, so that's just transmission. Here's the scattering object. And now as I start increasing the angle, start deviating from 180 degrees, the energy of the photons is decreased. and continues to be decreased. In this case, can't do the 180 degrees, but the more, now the photons, they're emitted in this direction towards you, but we're detecting, the detector is here, so we're detecting now photons scattered at 150 degrees roughly. So if I go back to reducing the angle, then the intensity, the energy of the photons increases. So their energy, that's the Compton effect, and that's actually a fairly important effect that we're going to use in the weeks to come. Okay, the third effect that I want to discuss is the photoelectric effect. So what we have here is an incident X-ray, and now this X-ray interacts with an inner shell electron. So it has sufficient energy to kick the inner shell electron out of its shell, so it has more energy than the binding energy, and that inner shell electron is being removed. So that is then produced. This is a so-called photoelectron is produced. And what we also have is then an outer shell electron, like we discussed last week. Last week we had electrons kicking out electrons of the inner shell. Now we have a photon doing the same thing. So now this creates a vacancy, the atom is in excited state, and an outer shell electron will fall into the inner shell and while it does that, it will emit characteristic X-rays or characteristic radiation. So the energy, in order to have the effect, the energy of the incident X-ray h nu must be bigger than the ionization energy of the electron in a particular shell, and we typically consider primarily K-shell electrons. So the energy of the incident photon must be equals the energy of the kinetic energy of the electron plus the binding energy of the electron. And what you actually then get is a cascade of emitting characteristic X-ray quanta. You can, of course, also have Auger electrons, but they are not so frequent in tissue with low Z. So the effect increases abruptly with the energy when it is slightly above the binding energy of the electron. Why is that? So if you don't have enough photon energy to overcome the binding energy, nothing happens. When you're then just there to kick it out of the shell, then it's getting absorbed, so suddenly the absorption is much higher. So you get a jump there. And then, as you go higher and higher, actually, the absorption decreases again. The absorption edge energy increases with Z. It's actually very low for most elements that we have in tissue, because the binding energy increases with Z. And so what we see here now is an example. This is the mass attenuation coefficient for barium and iodine. You see the absorption decreases, and then here you get this discontinuity. That's where the energy of the photon corresponds to the K-shell energy of the electrons. These are the so-called K edges. For tissue, you don't see the K edges because they are so low for diagnostic X-ray imaging. They're well below 20 kiloelectron volts, so we don't see them. So that's what you see in tissue. The effect goes down, and then again, the probability goes down with increasing energy. And incidentally, that's for the photoelectric effect is what Albert Einstein got his Nobel Prize in 1921. So now the fourth effect is pair production. And basically, pair production occurs when the photon energy of the incident photon is twice the rest energy of an electron. Okay, so then the photon carries so much energy that actually what happens due to an interaction with the electric field of the nucleus, it dies and converts itself into 2 electrons. And hence it's called pair production. You need 2 times the rest energy, so you need more than 1 mega electron volt for this effect to occur. The kinetic energy of the produced 2 electrons is equal to the initial energy of the photon minus their rest energy. And here's an example of Pair production, so we have an incident photon here, it interacts, it's in a magnetic field, so the electron is deviated. Actually, I said the wrong thing here. It's not two electrons you're producing, of course, you have to have neutral charge, so you need to have an electron and something positively charged, and that's the positron. Okay, so that's the E plus, here's the positron. So, and then, of course, you have here's the electron, here's the positron, they're deviated in the opposite sense because of their opposite charge. Fortunately, this effect is not important in bioimaging because we do not deal with energies in the mega electron volt range. So to come to the summary of the effects, this is coherent scattering, so that's Rayleigh scattering. Light does not change the wavelength, it's just deviated. We have Compton effect, interaction at the outer shell electron, it changes the wavelength, and it produces an unbound electron, or is ionizing. Photoelectric effect is absorption of the X-ray, and the electron is ejected from the inner shell. And pair production, here at some point, we get a positron and an electron. Okay, so now if we look at the sum of the effects, we can now look at the various effects. And this, notice here that the y-scale of the linear attenuation coefficient is logarithmic. And here on the x-axis, we have the energy of the photons in kilo-electron volt. We have Rayleigh scattering, which drops off very fast. We have the photoelectric effect. Here drops off also very fast. Then this effect here is the Compton effect. It varies less with energy of the photon. And then only above a mega electron volt, we're starting to see pair production becoming increasingly likely. So these are the individual contributions. And when you sum them together, this is your linear attenuation coefficient as a function of photon energy. And you can see it's a fairly complex function. Now, the good news is I've given you all the basic interactions. And the good news is 2 of them we can just forget for the biomedical applications. That's Rayleigh scattering and pair production. They're really not important. So the effects that we need to consider are the energies that we use for CT and SPECT, we're in this energy range, and for PET, positron emission tomography, we're at 500 kiloelectron volts. So, and in this range, we can see here, the effects that are important are photoelectric effect and Compton effect. And those are the 2 effects that are important for understanding the behavior of the linear attenuation coefficient. So just to round up the hour, I wanted to show this experiment of the cloud chamber. So we have so you should see it on the screen here. So we have a chamber here that's with saturated hydrogen vapor. And what you have here, what you see here, is a radioactive source that emits electrons. And the idea of the experiment is now to oversaturate the water vapor, and where the electrons come out, they will produce condensed vapor that you can see. Just like airplanes up in the sky, we see the airplanes streaking through. Now we've got the particles, and if you do it right, we'll have a very nice demonstration. It's a very short effect. Did you see it? No? And we'll have to give it a few seconds to do it again, but you should in principle see how they spread out, streaking effects. Anybody seen it? Some have. Shall I do it again? Okay. Should reset this. Usually it only works on the first try, this experiment. if it works. Okay, let's give it another try. You have to really watch carefully. You should see it. Okay? All right, so these are electrons made visible. They just streak through the oversaturated hydrogen vapor and produce condensation. It's essentially the same effect as for airplanes. Okay, with that we will break and resume in 15 minutes.